Welcome back to my YouTube channel. In this class I am going to discuss two numericals of P.K.Nag's engineering thermodynamics, and these two problems are based upon the concept of unsteady flow processes. Unsteady flow process is an important area and it is a tough one. Sometimes teachers find it difficult to clarify the concepts of students. So before starting, I must say one thing to all of you: please do subscribe to this channel and of course like it and share it to your friends. And in fact, I am going to discuss two problems, that is, one is 5.19 and later on 5.20. So two problems, and 5.19 has two bits A and B. The question is like this: you see, the internal energy of air is given at ordinary temperatures by U is equal to U0 plus 0.718 T, where U is in kilojoule per kg, U0 is any arbitrary value of U at 0 degree Celsius, किलोजूल पर केजी में है स्पेसिफिक इंटरनल एनर्जी स्मॉल यू, एंड टी इज द टेम्परेचर इन डिग्री सेल्सियस. ये जो स्मॉल टी है, टेम्परेचर इज इन डिग्री सेल्सियस. ऑल्सो फॉर एयर पी भी, पी स्मॉल भी, both are intensive properties, is equal to 0.287 multiplied by T plus 273, where P is in kilopascal and small v is in meter cube per kg, that is specific volume. And beta, that is an evacuated bottle, is fitted with a valve through which air from the atmosphere at 760 mm of mercury and 25 degrees Celsius is allowed to flow slowly to fill the bottle. If no heat is transferred to or from the air in the bottle, what will its temperature be when the pressure in the bottle reaches 760 mm of mercury? This is a case of charging. There are two types of problems we face in unsteady flow process. One is charging and discharging. In this case, this is a case of charging because the air enters into the bottle and no air leaves the bottle. In fact, only the mass is entering into control volume and no mass leaves the control volume in this particular case. And evacuated है, bottle evacuated है initially. But second bit में ये पूछा है, if the bottle initially contains 0.03 meter cube of air at 400 mm of mercury and 25 degrees Celsius, what will the temperature be when the pressure in the bottle reaches 760 millimeter of mercury? That is the supply line pressure. In fact, in the case A also, the process will continue unless and until the pressure inside the bottle reaches the pressure of supply line, that is 760 mm of mercury or 76 cm of mercury, which is standard atmospheric pressure. And then in the second case, बॉटल इवाक्वेटेड नहीं है. उस केस में टेम्परेचर कितना हो जाएगा बॉटल में वंस द प्रोसेस इज कंप्लीटेड, ये पूछा गया है. सो फर्स्ट बीट, there is a direct formula which we have already derived, and in the process of solving we will derive that once more, you see. So what is that formula? So you see, this is a simple case of charging. This is a simple case of charging. Only the fluid enters into control volume. You see, this is supply line. यहाँ से एयर आ रहा है, and here is the valve. Here is the valve which regulates the flow of air into this. Suppose this is a bottle. First bit में bottle is evacuated. So you see, this kind of problems, two principles are used. One is mass balance principle and another is energy balance principle. You see, the supply line pressure is 760 mm of mercury And what are the other conditions that is given in the this is only condition, that is pressure is given of the supply line air from which the air enters into the bottle. you know Initially the bottle is evacuated. That means the initial mass of this bottle is 0. We are solving first bit A. So you see, U is equal to U0 plus 0.718 t, small t. And we know that U is equal to 0 for air at, we can take it, can assume it, absolute टेम्परेचर 0 केल्विन पे इंटरनल एनर्जी सपोज 0 है. दैट मीन्स एट स्मॉल टी इज इक्वल टू 0 केल्विन, मतलब स्मॉल टी इज इक्वल टू -273 डिग्री सेल्सियस. मतलब 0 इज इक्वल टू U0 प्लस 0.718. इस इक्वेशन में अगर पुट करेंगे तो ये टी के प्लेस में वी विल राइट -273, फ्रॉम व्हिच this is equal to U0 minus 0.718 into 273. We know that at T is equal to 0 Kelvin, 0 Kelvin में absolute temperature 0 Kelvin में जो specific internal energy होता है वो 0 होता है. So this is the equation from which what we obtain is U0 is equal to 0.718 multiplied by 273. And we know that हमारा इक्वेशन तो ये है ना, ये सपोज इक्वेशन 1 है. U इज इक्वल टू U0, ये गिवन है, क्वेश्चन में गिवन है. U इज इक्वल टू U0 प्लस 0.718 इन प्लस ऑफ U0 आई विल राइट this 0.718 multiplied by 273 plus 0.718 t. This is equal to 0.718 multiplied by t plus 273. This is equal to 0.718. Degree Celsius, degree Celsius plus 273 is equal to Kelvin. T plus 273 is equal to capital T, that is when temperature is expressed in terms of Kelvin. So that is 0.718 multiplied by T. This is 0.718 multiplied by T. And again, but other condition is PV is equal to 0.287 T. So H is equal to U plus PV. In place of U I will write 0.718 T plus PV I will write 0.287 T, that is equal to 1.005 T. So हमारा जो स्पेसिफिक एंथैल्पी है 1.005 मल्टीप्लाइड बाय कैपिटल T, एंड U जो है 0.718 multiplied by capital T. We know that for an ideal gas U is equal to Cb multiplied by capital T and H is equal to Cp multiplied by T. So two principles are used for solving this kind of problem. One is mass balance. In mass balance, for control volume, this is your control volume, यहाँ only mass is coming in and no mass is leaving out. So this is a case of charging. We know that according to principle of mass balance, M in, and in fact it is better to analyze the unsteady flow process over a finite period of time rather than per unit of time. M in minus M out. Suppose M in is the total mass that has entered into the control volume during that process. M in minus M out is equal to delta MCV is equal to M2 minus M1. And you see, in this case M out is 0 and M1 is also 0. Why? Because initially the bottle is evacuated. So what we found is M in is equal to M2. This is your equation 1. M in is equal to M2. m2 is final mass. Once the process is completed, what is the mass of air inside this bottle? And m1, given in the question, that is evacuated, means initial mass in the bottle is 0. So min is equal to m2. According to energy balance principle, energy balance principle m in h in, neglecting the kinetic energy and potential energy of flowing fluid with respect to the specific enthalpy. When a fluid is flowing into control volume or exiting the control volume, three forms of energy are associated with that fluid. One is specific enthalpy, and the second one is specific kinetic energy and specific potential energy. And in this case, we can neglect this kinetic energy and potential energy of flowing fluid, because those are quite negligible as compared to specific enthalpy, and in most of the cases they are neglected. And in this problem, no velocity or no any other potential energy term is given in the question, so we can neglect it. m in h in plus q, ये इनसाइड में एनर्जी हुआ, माइनस m out h out प्लस WCB, ये हो गया हमारा E in, ये हो गया हमारा E out, इक्वल टू डेल्टा ECB, change in energy of control volume. And we can also neglect the change in potential energy and kinetic energy of control volume. That means EK and EP को neglect कर देंगे, तो ये हो गया हमारा डेल्टा U of control volume, that is equal to m2 u2 minus m1 u1, where m2 is the final mass of air in the bottle once the process is completed. m1 is the initial mass, and in this case m1 will be 0, because it is given that this is an evacuated bottle. So these two terms are also 0. There is no mass leaving the control volume. You see, this in this case only mass is entering into the control volume, and this process can be assumed to be a uniform process, so that during the whole process neither temperature nor pressure of this air in the supply line changes, and those properties can be assumed to be constant. So m2 u2 minus m1 u1, and these two terms are 0. शाफ्ट तो लगा नहीं है यहाँ, so WCB is 0, and it is given that the bottle is insulated, so Q भी हम 0 ले सकते हैं. So now the equation reduces to, this is suppose equation 2, this is the energy balance equation, m in h in equal to m2 u2. This is your equation 2, and from equation 1 and 2, combining the equations 1 and 2 together, what we found is, in place of m in I will write m2 h in equal to m2 u2. यहाँ से क्या आ गया, h in is equal to u2. h in we know that cpt in is equal to CB, T2 is final temperature, from which I can find what I can find is CP divided by CB T in, that is gamma T in, it is equal to 1.4. T in is given to be जो सप्लाई लाइन का टेम्परेचर यहाँ लिखा हुआ है, सप्लाई लाइन का टेम्परेचर एयर फ्रॉम द एटमॉस्फेयर एट 760 mm mercury and 25 degrees Celsius. 25 degrees Celsius. So we have to convert that into Kelvin. 273 plus 25. This much Kelvin is T2, final temperature of air in the bottle after the process is completed. So it comes out to be 1.4 multiplied by 298, that is equal to 417.2 Kelvin or 144.2 degree Celsius. So this is the answer, 144.2 2 degree Celsius. We can directly remember this formula, that is when any tank or bottle is evacuated and the process continues, the charging process continues, any fluid enters into the control volume from a supply line, unless and until the pressure inside the tank or bottle becomes equal to that in the supply line, then the temperature increases. Temperature inside that control volume may be tank or may be bottle, increases, and that is equal to gamma multiplied by the supply line temperature. Temperature inside the tank or bottle will be equal to gamma, ratio of specific heats of that fluid multiplied by the supply line temperature. That formula we can remember, but we can't blindly apply this formula for every case. Suppose in a case there is mentioned that heat supply is taking place, then we cannot apply this formula. So T2 is equal to gamma T in, applicable only in the case in which the initially कोई भी mass नहीं है and the conditions are insulated and the tank is insulated, no heat interaction takes place. Shaft work तो नहीं है in this case of problems. No electrical work is there. If electrical work is there, the whole problem will change. So now this you can also remember this formula, but we can't afford to apply this formula blindly. So we have to see the conditions, then only we can apply this formula. Evacuated है तो ये easily apply हो सकता है, and insulated and evacuated होगा तो ये apply कर सकते हैं. And in the second bit ये evacuated नहीं है. In this case, if the bottle initially contains 0.03 meter cube of air at 400 mm of mercury and 25 degrees Celsius, what will the temperature be when the pressure in the bottle reaches 760 mm of mercury? तो इनिशियली अगर कुछ है तो प्रॉब्लम हमारा the answer will be different. In the first case, it was given that the bottle was initially evacuated. So in this case some mass was there, so m1 will be p1 v divided by rt1, and that is equal to p1 हमको निकालना है 400 mm of mercury, 400 mm of mercury, and volume is given 0.03 meter cube. r तो है 0.287 में, kilojoule per kg Kelvin. We know that r for air is this much, kilojoule per kg Kelvin. T1 is given to be 25 डिग्री सेल्सियस, मतलब हमको कन्वर्ट करना पड़ेगा 273 प्लस 20 298 केल्विन. सो यहाँ क्या करेंगे हम, फर्स्ट ऑब्जेक्टिव इज टू कन्वर्ट दिस प्रेशर in terms of kilopascal, which is in terms of millimeter of mercury. You have to convert it into the kilopascal. So first हम प्रेशर को कन्वर्ट करेंगे. इनिशियली इन दिस पर्टिकुलर प्रॉब्लम बॉटल में इतना मास है, ये जो सप्लाई लाइन है यहाँ से जो आ रहा है बॉटल के अंदर, पहले इनिशियली कुछ मास है यहाँ पॉइंट, ये जो वॉल्यूम है तो 0.03 मीटर क्यूब, और जो हमारा प्रेशर है 400 mm मर्क्यूरी, सम मास है. सो उस मास को निकालने के लिए प्रेशर को निकालना पड़ेगा. सो प्रेशर करस्पॉन्डिंग टू 400 mm of mercury, 400 mm of mercury is equal to, pressure is equal to rho into g into h. Rho is the density of mercury. Density of mercury is 13600 kg per meter cube multiplied by 9.81 meter per second square. Rho into g into h. h is हमारा 400 mm, तो इसको हम मीटर में कन्वर्ट करेंगे. ये हो गया हमारा, ये जो आंसर आएगा वो पास्कल में आएगा. इसको अगर हम डिवाइड करेंगे 1000 में तो किलो पास्कल में आएगा. क्योंकि ये केजी पर मीटर क्यूब है, एसआई यूनिट है, एसआई यूनिट ऑफ प्रेशर इज पास्कल, सो ये पास्कल में आएगा। लेकिन हम वी हैव टू कन्वर्ट दिस इनटू किलो पास्कल सिंस इन दिस फार्मूला आइडियल गैस इक्वेशन आर तो किलो जूल पर केजी केल्विन में है। So we have to convert this pressure into kilopascal, and in terms of kilopascal this is 53.366 kilopascal. So mass m1 will be, initial mass in the bottle will be 53 point, this is pressure 366 kilopascal into volume is 0.03 meter cube, and R is 0.287. Now R for air you have to remember, you are expected to remember R and gamma for air, Cp and Cv also. This is equal to 0.0187 kg. Initially इतना mass of air था, and हमारा जो इक्वेशन मास बैलेंस का जो इक्वेशन होगा इन दिस केस विल बी m in equal to m in minus m out. This is the principle of mass balance, m2 minus m1. यहाँ कुछ भी मास आउट नहीं जा रहा है, तो प्रिंसिपल ऑफ दिस इज सिंपली प्रिंसिपल ऑफ मास बैलेंस, m in minus m out is equal to delta mcb, that is m2 minus m1. m2 is the final mass of air inside the bottle after the completion of the process. After once the pressure inside the bottle reaches the supply line pressure, that is 760 mm of mercury, the process will stop. So m2 minus m1, in this case m1 cannot be 0, so m1 is this much, m2 minus 0.0187. so m2 we can calculate, m2 is equal to P2 V remains same and RT2 T2 तो हमको निकालना है ना, T2, और प्राइम ऑब्जेक्टिव ऑफ दिस क्वेश्चन इज टू दिस क्वेश्चन रिक्वायर्स द फाइनल टेम्परेचर निकालने के लिए. सो T2 वी हैव टू कैलकुलेट, T2 वैल्यू ऑफ T2 वी डोंट नो, T2 विल बी कैलकुलेटेड, सो वी हैव टू एक्सप्रेस M2 इन टर्म्स ऑफ T2 ओनली. P2 हमारा है 700 सप्लाई लाइन प्रेशर के साथ. व्हेन द प्रोसेस विल स्टॉप ओनली व्हेन द प्रेशर इनसाइड द बॉटल रीचेस द सप्लाई लाइन प्रेशर. सप्लाई लाइन का प्रेशर जो है ये है, टेम्परेचर है 25 डिग्री सेल्सियस एंड 760 mm ऑफ मर्क्यूरी, ये दिया हुआ है क्वेश्चन में. सो फर्स्ट वी हैव टू कन्वर्ट दिस 760 mm टू in terms of kilopascal. So P2 multiplied by 0.03 divided by 0.287 into T2 तो निकालना है हमको. So P2 हमको निकालना है. P2 is equal to rho into G into H, that is 13600 9.81 760 divided by 1000. Once again it has to be divided by 1000 to find the pressure in terms of kilopascal, that is equal to 101.396 kilopascal, that is the standard atmospheric pressure, 101.396 kilopascal. Initial pressure was inside the bottle was initial pressure था 53.366 kilopascal, and after the pressure rises to 101.396 kilopascal, the process will stop. So M2 will be final mass will be 101.396 multiplied by P2V, V तो सेम रहेगा 0.03 divided by 0.287 multiplied by 2 T2 is the final temperature which is the desired answer. This is equal to 10.598 divided by T2. Now the mass balance equation becomes M in. Now the mass balance equation is M in minus M out is equal to M2 minus M1. So M in, M out तो जीरो रहेगा यहाँ पर, कुछ भी मास बाहर नहीं जा रहा है, is equal to 10.598 divided by T2 minus M1 is 0.0187 kg, 0.0187 kg M1. सो ये हमारा हो गया इक्वेशन 1, प्रिंसिपल ऑफ मास बैलेंस. एंड अकॉर्डिंग टू प्रिंसिपल ऑफ एनर्जी बैलेंस, M in H in प्लस Q, ये हो गया हमारा E इन पे आ रहा है, कंट्रोल वॉल्यूम को इतना एनर्जी आ रहा है, माइनस M आउट H आउट प्लस WCB, ये E आउट हो जा रहा है. अगर किस केस में होगा आउट हो रहा है तो ये होगा, लेकिन इन दिस केस दिस टू टर्म्स आर जीरो, दिस वन इज जीरो एंड दिस वन इज ऑल्सो जीरो, क्योंकि कोई भी मास नहीं बाहर नहीं जा रहा है, नॉर एनी WCB वर्क इज देयर. सो इज इक्वल टू डेल्टा UCB is nothing but M2 U2 minus M1 U1. This is our equation and this is 0. So now the equation is M in H in equal to M2 U2 minus M1 U1. So this I can write H is equal to CPT in equal to M2, U is equal to CB multiplied by capital T, CBT2 minus M1 CBT1. इससे हम T2 निकाल सकते हैं, एंड दिस इज योर इक्वेशन 2. इक्वेशन 1 एंड 2 को सॉल्व करके हमको T2 निकालना है बस. सो in place of M in I will write 10.598 divided by T2 minus 0.0187 multiplied by 1.005 into T in is 25 डिग्री सेल्सियस, लेकिन यहाँ इसको एब्सोल्यूट टेम्परेचर में कन्वर्ट करने के लिए 273 ऐड करना पड़ेगा, दैट इज 298 is equal to M2 के जगह I will put M2 is 10.598 divided by T2 multiplied by 0.718 multiplied by T2 minus M1 is 0.0187 multiplied by 0.718 multiplied by T1 is ये जो है इनिशियली द एयर जो बॉटल में है उसका भी टेम्परेचर 25 डिग्री सेल्सियस, तो उसको अगर केल्विन में कन्वर्ट करेंगे 298 होगा. ये इक्वेशन को सॉल्व करके हमको यहाँ ये T2 कैंसिल हो रहा है, तो ये राइट हैंड साइड में कुछ वैल्यू आ जाएगा, वो होगा 7.6099 माइनस 4.0011. You can calculate, and this is equal, you can check it out, this is equal to 3.6088. सो यहाँ से हम T2 निकाल सकते हैं इजीली, और 10.598 divided by T2 minus 0.0187 is equal to 3.6088 divided by 1.005 multiplied by 298, वो आ रहा है 0.01204. यहाँ से हम T2 निकालेंगे और 10.598 divided by T2 is equal to 0.01204 plus 0.01 5.87 is equal to 0.03074। यहाँ से हम T2 निकालेंगे। सो T2 निकालेंगे हम। T2 इज इक्वल टू 10.598 divided by 0.03074, that is equal to 344.7625 Kelvin, and in degree Celsius this will be 71.76 degrees Celsius. And when the bottle was initially evacuated, the temperature rise होता था 144.2 डिग्री सेल्सियस तक, and when there is some mass in the beginning of the process inside the bottle, temperature हो रहा है increase हो रहा है up to 71.76 डिग्री सेल्सियस। सो दैट इज ये केल्विन पे है। अगर डिग्री सेल्सियस में इतना होगा, ये T2 है हमारा, जस्ट यहाँ से 273 माइनस करेंगे। ये 5.19 का बीट ए एंड बीट बी। So now we'll discuss the problem number 5.20. A pressure cylinder of volume V contains air at a pressure P0 and temperature T0. Temperature T0. It is to be filled from a compressed air line maintained at constant pressure P1 and temperature T1, so that the temperature of the air in the cylinder after it has been charged to the pressure of the line is given by T is equal to gamma T1 divided by 1 plus P0 by P1 multiplied by gamma T1 by T0 minus 1। ये एक हमको ये प्रूव करना है। आफ्टर द प्रोसेस इज ओवर, व्हाट विल बी द टेम्परेचर इनसाइड द सिलेंडर। इस केस में भी इवैक्यूएटेड नहीं है। इनिशियली सम प्रेशर इज देयर, सम अमाउंट ऑफ एयर इज देयर, वॉल्यूम भी है, एयर प्रेशर P0 एंड टेम्परेचर T0 पे है। लेकिन जो सप्लाई लाइन है उसका प्रेशर है P1 एंड टेम्परेचर है T1। सो वंस द प्रेशर ऑफ द cylinder reaches the supply line pressure, the charging process will stop, and at that time what would be the temperature of air? That T will be gamma T1 by this much. So we have to prove that. You see, this is also a case of charging. So this is your supply line. Here is a valve. This is the cylinder. यहाँ इनिशियली प्रेशर है P0, टेम्परेचर है T0, and this is your supply line. And during the process, this supply line pressure and temperature will not vary, and they are assumed to be constant. This is suppose P1 and T1, and these are assumed to be constant because the flow is assumed to be uniform. यहाँ भी जितना होगा प्रेशर टेम्परेचर ऑफ दिस एयर, यहाँ भी उतना होगा। And initially the pressure inside the cylinder is P0 and the temperature inside the cylinder is T0, and the process will continue, and this will air will enter into cylinder up to the time when the pressure inside the tank rises to this pressure P1. When the pressure inside this is a cylinder, pressure inside cylinder reaches the P1, the process will stop. So now same way, whatever the procedure we adopted while solving the 5.19, this is the same case, only there were numerical values, and in this case we have to derive that, and in fact we have to prove that T is equal to this much. So you see two principles are only used in this case of problem. First is principle of mass balance, principle, and this is the boundary, and this is the control volume. This is the your control volume, mass balance. M in minus M out. M in is the total mass that has entered, mass of air that has entered into the cylinder during the whole process. M out is the total mass of air that has left the cylinder during the process. In fact, this is 0 because there is no mass leaving this cylinder. Only the mass is entering from the supply line into the cylinder, is equal to delta mcv is equal to m2 minus m1. m2 is the final mass. Once the pressure inside the cylinder reaches the supply line pressure, the process will stop, and at that point of time, what is the mass of air inside the cylinder? That is m2, and m1 is the initial mass of air in the cylinder, m2 minus m1. So this is equal to m2 hoga PV by MR. PV is equal to MRT. Ideal gas equation will be put here. You see, final pressure will be P1. Volume suppose is the V. Volume ये तो दिया हुआ है ना क्वेश्चन में, प्रेशर सिलेंडर और वॉल्यूम भी, मतलब P1 V डिवाइडेड बाय RT. फाइनल टेम्परेचर T है, जिसको हम T1 और T0 P1 P0 टर्म में एक्सप्रेस करना है. सो P1 V डिवाइडेड बाय RT माइनस P0 भी डिवाइडेड बाय RT0. ये इनिशियल प्रेशर, इनिशियल टेम्परेचर है इनसाइड द सिलेंडर. यहाँ से हम निकालेंगे where capital T is the temperature of air in the cylinder after it has been charged to the pressure of the line. Pressure of the line is P1. P1 is greater than P0. That's obvious. And once the pressure rises and reaches at the P1, then the process will stop. So Min is equal to this much, is equal to, I can take V by R common. So that will be P1 by T minus P0 by T0. सपोज दिस इज योर इक्वेशन 1. एंड एनर्जी बैलेंस में क्या आएगा? एनर्जी बैलेंस में एम इन एच इन प्लस क्यू, ये होता है यू इन माइनस एम आउट एच आउट प्लस डब्ल्यू सी बी इज इक्वल टू M2 U2 माइनस M1 U1. यहाँ ये दोनों टर्म 0 है, ये भी 0 है, क्योंकि it is also given that insulated. A pressure cylinder, if you read at the question, it is given that nothing is mentioned about the heat. So that means heat flow. So that means you have to assume that this term is also 0. Q in is also 0. So now the equation is this much. So this is equal to, in place of M2 I will write P1V divided by RT. In place of U I will write, for ideal gas, air is an ideal gas, U is equal to CVT, CV multiplied by capital T, absolute temperature of air at the final state, minus M1 is P0V divided by RT0 multiplied by CV T0. यहाँ से T कैंसिल हो जाएगा, T0 कैंसिल हो जाएगा, ये आ जाएगा P1V मल्टीप्लाइड बाय CV बाय R माइनस P0V मल्टीप्लाइड बाय CV बाय R इज इक्वल टू P1 माइनस P0V multiplied by CV by R. So you know CV by R, Cp minus Cv is equal to R for any ideal gas. If you divide both sides by Cb, it will become Cp by Cb minus Cb by Cb is equal to R by Cb, or gamma minus 1 equal to R by Cb. You know gamma is the ratio of specific heat. So मतलब यहाँ से Cb by R होगा, R by Cb अगर इतना है, Cb by R होगा 1 upon gamma minus 1, 1 upon gamma minus 1. And I will put this here, P1 minus P0 multiplied by 1 by gamma minus 1. V is there. सो यहाँ होगा P1 माइनस P0 मल्टीप्लाइड बाय V डिवाइडेड बाय गामा माइनस 1। ये हमारा हो गया इक्वेशन 2। सो इक्वेशन 1 ये था एम इन इज इक्वल टू V बाई आर मल्टीप्लाइड बाई P1 बाई T माइनस P0 बाई T0। एंड इक्वेशन 2 ये हो गया हमारा एम इन एच इन इज इक्वल टू P1 माइनस P0 V डिवाइडेड बाय गामा माइनस 1। फ्रॉम इक्वेशंस 1 and 2 we get what we get is, in place of m1 I will write V by R from equation 1 P1 by T minus P0 by T0। ये हो गया हमारा एम इन, लेकिन यहाँ एम इन ये हो गया, एच इन में हम पुट करेंगे CP T1, क्योंकि सप्लाई लाइन का जो प्रेशर है वो तो कांस्टेंट रहता है एंड दैट इज गिवन टू बी T1। सप्लाई लाइन का टेम्परेचर T1 है, प्रेशर P1 है। सो H होगा CP T1। एम इन एच इन इज इक्वल टू P1 माइनस P0 मल्टीप्लाइड बाय V डिवाइडेड बाय गामा माइनस 1। यहाँ से CP T1 डिवाइडेड बाय R, ये V भी कैंसल्स आउट। P1 बाई T माइनस P0 बाई T0 इज इक्वल टू P1 माइनस P0 बाय गामा माइनस 1। यहाँ से P1 बाई T माइनस P0 बाई T0 इज इक्वल टू P1 माइनस P0 बाय गामा माइनस 1 डिवाइडेड बाय CPT1 बाय R और मल्टीप्लाइड बाय R बाय CPT1 इज इक्वल टू P1 माइनस P0 बाय गामा माइनस 1। In place of R by CP I will write R by CP will be, you see here CB by R is this much or CB is equal to R by gamma minus 1. So CP will be gamma R divided by gamma minus 1. So R by CP will be gamma minus 1 by gamma। R by CP will be, यहाँ से CP is equal to gamma R by gamma minus 1, तो R by CP होगा gamma minus 1 by gamma and already T1 is there, so gamma T1 हमको लिखना पड़ेगा। so ये हो गया P1 माइनस P0 डिवाइडेड बाई, ये गामा माइनस 1 कैंसल्स आउट, सो गामा T1। लेकिन हमको T को एक्सप्रेस करना है इन टर्म्स ऑफ P1 P0 एंड T1 T0। सो T टर्म को एक साइड पे ले आएंगे एंड रेस्ट ऑफ द टर्म्स विल बी ब्रॉट इनटू अनदर साइड एंड द टर्म इन्वॉल्विंग T विल बी पुट इन वन साइड ओनली। सो और यहाँ से आ गया P1 बाई T इज इक्वल टू P0 डिवाइडेड बाई T0 प्लस P1 माइनस P0 बाय गामा T1। एलसीएम हो जाएगा गामा T1 T0 P0 गामा T1 प्लस P1 T0 माइनस P0 T0। So that is equal to, from that T is equal to gamma T1 T0 P1 divided by P0 gamma T1 plus P1 minus P0 T1। यहाँ से लेकिन हमको ये एक्सप्रेस करना है दिस लाइक दिस, टी इज इक्वल टू गामा टी वन। सो यहाँ हमारा है गामा टी वन टी जीरो पी वन। सो वी हैव टू डिवाइड बोथ न्यूमरेटर एंड डिनोमिनेटर by the term t0 p1, so that in the numerator it will come out, gamma t1 will come out. So dividing both sides, both numerators and denominator by t0 p1 in right hand side of equation is equal to gamma t1 divided by p0 gamma t1 divided by p1 t0 plus p1 t1 minus p0 t1 divided by p1 t0 माइनस p1 t0, ऐसे लिख सकते हैं। ये हो गया हमारा गामा t1 डिवाइडेड बाय p0 by p1 इंटू गामा t1 by t0 प्लस p1 ये हो गया हमारा p1 t0 माइनस p0, ये हमारा t0 है, सॉरी दिस इज t0, दिस इज t0। सो p1 t0 बाय p0 p1 t0, दिस इज 1 माइनस ये t0 कैंसल्स आउट, दिस टर्म इज p0 बाय p1 इज इक्वल टू गामा t1 डिवाइडेड बाय p0 बाय p1 कॉमन ले आएंगे तो गामा t1 बाई t0 ये -1 +1। इसको हम ऐसे भी लिख सकते हैं गामा t1 डिवाइडेड बाय 1 प्लस p0 बाई p1 मल्टीप्लाइड बाय गामा t1 बाई t0 -1। ये तो इसी एक्सप्रेशन को दिया था प्रूव करने के लिए। t इज इक्वल टू गामा t1 divided by 1 plus p0 by p1 multiplied by gamma t1 upon t0 -1. So thank you for watching.